colloquium of the semester. Our speaker today is Salah Mohammed, who I expect you all know. He's a faculty member in our department and recently returned from a semester-long engagement at the Institute for Mathematics and its Applications. We'll let him say his piece.
Okay, thank you, Wesley, for the introduction. I'm happy to give this talk today. So I'm going to say a little bit about fluid models in stochastic framework. And these are the fluid models are very classical. They include the Burgers equation and Navier-Stokes equation in 2D, well, not 3D. Too hard. So I will tell you a little bit about the dynamics of these models from a topological point of view, not from a physical point of view, from a topological point of view. So I will want to acknowledge that support from NSF and also joint work with Tusheng Zhang. Tusheng Zhang is in Manchester, in England. So this is a joint work with him. Okay, so what I will give you is a survey of recent results on stochastic Burgers equation. We abbreviate it, say SBE, stochastic Burgers equation, and 2D stochastic Navier-Stokes Equation, SNSE. If you see SBE, SNSE, remember Burgers and Navier-Stokes. And we will assume that we have noise in the system, okay, like external noise in the system. Okay, so what we're gonna aim to is to establish the stable manifold theorem for these equations, and the local invariant manifold theorem, and the global invariant flat theorem. So these are topological characterization of the set of initial functions according to the stability or instability of the solution of the stochastic partial differential equation. Okay, and you'll find that there is a very nice, actually, topological structure lying behind that, even though the equation look quite complicated. And we will use infinite-dimensional multiplicative ergodic theory techniques to do that. So these techniques are developed by David Rouel in France, and also some of them I developed with myself and Tusheng Zhang and Huazhong Zhao. Huazhong Zhao is in Loughborough in England, okay? And Tusheng Zhang is in Manchester. Okay? So this is the work by Rouel is a very difficult work. Okay, this appeared in the Annals of Math, and it's a very deep work, but it fits nicely in this step, even though you didn't have that in mind, but it fits very well here. And the results go beyond issues of well-posedness and existence of invariant measures. So in physics, usually, or in applied mathematics, people look at the differential equation, whether it's stochastic or not, and then they say, does it have a unique solution? Okay, does the solution exist? Is it unique? Okay, and how does the solution depend on the initial condition? So that's well possible. So we will develop that on the way, but we are looking for long-term behavior and structural stability after, beyond existence and unity. Okay. All right, so the methodology that we're going to use is infinite-dimensional perfect cocycles in Hilbert space. I will explain to you what a cocycle means. A Hilbert space, I assume almost all of us know roughly, essentially what a Hilbert space is. It's a nice infinite-dimensional space with a good geometry. From there, we take Rouel's spectral theory. So Rouel developed a spectral theory for this compact linear cocycle. Okay, in Hilbert space. The Hilbert space essentially would be like for the equation, would be the space of initial conditions, initial functions. So you put some Hilbert space structure. It's infinite dimensional, but it has nice geometry so that you can apply the word spectral. And then we look at the issue of hyperbolicity of a stationary point. Now, a stationary point would be like an equilibrium for the equation. Okay, it's an equilibrium solution. And then you say, how does this, is it hyperbolic? That means, is there some parts of the solution that go away from the initial condition and some parts of the space that converge to it? Okay. And in fact, that's true in both modes. It cannot be true. And then you look for invariant manifolds for infinite dimensional Cocycle Hilbert space. So this here, these are manifolds that are nonlinear and embedded in the space of initial condition. So you look for those invariant. Invariant means that if you sit on the manifold, which is random, cannot be random, you essentially stay on if you follow the solution, the trajectory. And we prove that these exist. They are actually submanifolds of the Hilbert space where they are invariant, randomly invariant. And the cocycles, of course, are generated by solutions of the stochastic Burgers equation and the stochastic Navier-Stokes. So this methodology that we have here captures both models in one shot. Okay? All you have to do is just check the conditions, and you find that they're all satisfied. Okay, and so in particular, you get local stable and unstable manifold, invariant manifolds, and global invariant flags for the two models. Okay, so let me now give you a little bit of a structure of dynamics in Hilbert space, okay, in stochastic dynamics in Hilbert. So if you look at finite dimensions, there is a good deal of literature. Ludwig Arnold, Impler, Michel Chodzao, myself, a lot of people work on the finite dimension stochastic dynamics. So this is fairly well established, it's been around for some time. Now, in the stochastic partial differential general framework, there is some work by Duan and Lu and Schmarkos in Germany, and they assume you have a global Lipschitz nonlinearity in the equation, which is globally Lipschitz. So that will exclude Burgers equation and Navier-Stokes equation, because you have quadratic nonlinearity in both. So you can't do that. You cannot apply that. So, and also because the noise is also one-dimensional. So this doesn't quite apply. Okay. And now here is the basic idea, the idea of an infinite dimensional cocycle, and we would show that it is central to the models we are looking at. Okay, so I'm going to now give you a little bit of formalism of what is the setting structure. Okay, we start with familiar real line, okay, and then the positive numbers, real numbers, and then we have the probabilistic structure. You get a space of functions of paths from R to R of all continuous paths, and they vanish at zero, and we call these paths Brownian paths, because you put on that a classical measure called Wiener measure, you put it on the space of paths. So this is a probability measure, has very nice, well-developed properties, very well understood, and we use it in our setting for the noise, for the outside noise that you put in the system. And the sigma algebra, the Borel sigma algebra, here you have, of course, this is a topology, given a topology of uniform convergence and factor, and then that topology will generate a Borel sigma algebra, okay? And we complete it, so we put all sets of measures 0 in there. We don't have to worry about that from the beginning, okay? And as I said, it will give you this all evaluations. Omega is a path, so it goes from omega, which is space of paths, into the reals. And then you have this setting, which is omega, and then the sigma algebra, and then this is a sigma algebra up to time t. So you just generate sigma algebra up to time t, okay, and you call it f sub t, and that's Wiener. So this is the classical. Okay, now you have a shift remember, omega are paths. So what do you do here? You say for each time t and each path, I translate it by s and then shift it back so that it starts at 0. So this subtraction here just says that when s is 0, theta t of omega is 0. Okay, so it takes something that vanishes at 0. Okay, so we call it Wiener shift. One of the properties of the Wiener shift is that it preserves the measure. So if you take the measure here, p, and you push it over with theta, it's the same measure, exactly. Okay, now here is a very important concept of perfection. And this basically tells you that statements that you make are made universally in omega. That means if you take a set of propositions and you parameterize by omega, you say this set of propositions holds perfectly in omega if there is a sure event, there is a set of full measure which is invariant under theta and for which p omega holds for every omega in that set. So this set you choose a priori from the beginning and it works all the time. So you might as well say every statement we make is true for every omega, which is a very strong statement, because it didn't say that you have to have it almost everywhere, but it's everywhere as long as you are inside this set of full measure. So you might as well throw the rest. Okay, throw the rest away.
So sure event means full measure?
Sure event means full measure, okay. But here it's kind of almost sure, but not in the sense that omega star is universally defined from the beginning, and you stick with it for every step. Okay. And all the statements you're going to make are true perfectly. Okay, will be true perfectly. And it turns out that this is a non-trivial property in infinite dimension setting. In finite dimension, this is it's well established. You always can get it because you have Kolmogorov theorem. And in infinite dimensions, the theorem of Kolmogorov, which is well known, fails, breaks down. So you have to do it by hand. You look at each model and do it by hand. That you find the omega star. Okay, now E is a real Banach space. Okay, and then the Borel sigma algebra of E, and then the operators, the space of bounded linear operators from E to E. The strong topology. Strong topology means, as opposed to the operator topology, is the one that evaluations are continuous. Okay? So evaluations from T evaluate at any f. This mapping here is continuous. And then we look at the sigma algebra generated by this strong topology. Okay? Now, stochastic process is we have a process parameterized by the reals and the omega, and then goes into the linear operators. It's strongly measurable if you have this combination of measurability, okay, with respect to the Borel sigma algebra with a strong topology. Okay, so this is a kind of technicalities, but for well theory requires this strong measurability. Okay, and it's good enough because it's a weak condition. Okay, so here is a positive integer. Epsilon is something between 0 and 1, and then E and N are real Banach spaces with these norms. And then we look at the multilinear mappings. So we'll use this notation in the statement of the theorems. So this is a multilinear map, okay, from E cross E cross E to K up to N, okay. And we give it a norm like this, just like the operator norm that we do all the time. And notation simple, LKE is the same as LKEE. And then we have regularity. This is important here because it takes care of the regularity of the stable and unstable manifolds. So when we construct the manifolds, we are talking about regularity of this type, CK epsilon. That means you have K Frechet derivatives, and the K Frechet derivative is whole dot continuous with respect to epsilon. Okay? It turns out that the Berger equation has K equal infinity. So it's very smooth. Manifolds and the Cocycle is very smooth. The Navier-Stokes is C11. So it's differentiable once up to Holder continuity. Derivative is Holder continuity. Lipschitz continuity. Which is pressure derivative, and so this is regularity. You think of this as type of regularity. Okay, and now you have this space, dk epsilon from G to N, and you can give it this norm. This is a standard classical norm. Okay, here is the derivative up to K, and here is the Holder type, little bit of epsilon beyond K. Okay, and this is known to be a nice Banach space. Okay, if C infinity is Ck for all K, and it's all derivatives bounded on it. Okay, now let us look now at the idea of the dynamics now. Now we're going to introduce what is the dynamics we are going to look at. The dynamics is encoded in this Ck epsilon cocycle, perfect cocycle. What is a cocycle? It's a function or a mapping parameterized by three objects. Time, the space, the Hilbert space, and the chance, omega. Okay, but it has a few properties, very nice properties. First of all, no matter how you turn it around, it's nice. Okay, so if you fix omega, okay, and you think of it as a function of t and f, then it's continuous. It's geometric continuous. If you fix t and omega, then and think of it as a function of f as the initial condition, so to speak, it's Ck epsilon. So it's very differentiable and very nice. Okay, however you look at it. And now here is the dynamics. Here's the dynamics. Now this dynamics, it's not quite a semigroup. Okay, because you see, it's not really a random semigroup. It's what you call a cocycle. That means you have us omega like this as a function of f, but then you compose it not with ut, but you shift the omega with the Wiener shift. So you watch out where you are probabilistically, and then you apply ut, and you get the same result as ut plus s, perfectly in omega. For each omega in that universal set, this identity works. Okay, so it's a very strong result, very strong requirement. Okay. And then of course, the initial condition, if t is 0 and you are at f omega, you capture f. So that means you start at f. Okay, this is a very natural condition. Okay, now let me draw a picture for you, this one. So if you like a little bit of geometry, this is a mixed probability. Here is omega, is your base space, base manifold, the base space, you just call the manifold. And here are your fibers. The fibers are the Hilbert space, the initial conditions, and you select these according to the Wiener measure. Okay, you fix them up from the probability space according to Wiener measure. Okay, and then you say, I put the mappings. Down here, I have the theta, the Wiener shift, followed by another one, the T2. And here I have the cocycle, acting on the fibers here, the vector, the random vector bundle, if you want to call it that way. So you go like this. But here, you don't have T2, but you have to shift it because you are in theta T1. And then you compose this mapping with that mapping. Okay, and see what you get. Okay, you get a single path. Starting here, going over here, and then apply this mapping, you get here, and you get the same answer as if you went from here straight to here with the composition. The same path. It's not with probability, but with the same omega. So you see how this goes? Here is your f. You follow the cocycle or the group, so to the semi-group, time t1 with the f omega, and then you apply this part to this, and you get this for every omega, for the same omega, in a universal, in a perfect world. Okay. Okay. What we're going to do is to capture the dynamics of the Burgers equation and Stochastic Navier-Stokes equation via four perfect cocycles on suitable Hilbert space. So we design the Hilbert space and the cocycle so that it fits both of them. Each one has a different cocycle, but they all satisfy the same ergodic theorem. Okay, so let me begin by showing you the oscillatic Ruel spectral theorem for linearization of a cocycle along a stationary. So you take a cocycle and you take a stationary point, and then you, because the cocycle is differentiable, differentiate derivative, you can differentiate along the stationary solution, and you have a nice spectral theorem. I'm going to show you what the theorem looks like. It belongs to David Ruel that I mentioned. Okay, so what is the stationary point? What is the equilibrium? Equilibrium is a random point. Now you have this Hilbert space, and we have the points randomly moving on that, and you have the cocycle acting on that. Now we take a random point on the Hilbert space, and we say that it's invariant if you have this property. See how it looks? So this is the cocycle, ut, and now here is a random point. You plug it in instead of the f, and what it does, it generates the y. So this is the dynamics here. You're plugging into the equation, and you read out the solution. What you see is the original distribution, but only shifted by an invariant shift. So this will tell you that when you plug y omega into the solution, you get a stationary process, because theta, you see theta t leaves Wiener-Magellain invariant, and you are just plugging into some fixed number, so it has the same distribution. And that's the best way to describe equilibrium in this dynamic setting. And it's pathwise. This is a perfect state for each omega. So you don't have to deal with any measures, okay? You just work on the space itself, okay? And for each omega you can do it. So there is a stationary point like this. And in particular, if you have a stationary point of the cocycle, then its distribution is an invariant measure for the process. So the process itself has an invariant measure, and you can capture the invariant measure just by looking at the distribution of y. Okay, now one other nice thing about this is that, remember, this u is differentiable, pressure differentiable, so you can follow the cocycle, the stationary point y omega by differentiating. You see, this derivative here is with respect to, of course, to the middle variable, because everything else is not differentiable, okay? You know the u is differentiable, ck epsilon here. And so if you plug in y omega, you can differentiate pressure derivative. Pressure derivative is a linear operator from the space itself, from h to h. And it turned out that because of this property here, the differentiation will give you another cocycle, linear cocycle. Just by if you go back to the composition, the Cocycle property, and you apply the derivative to that, which is apply the chain rule, this comes out right. If you apply the chain rule to the Cocycle property, you can immediately see that this is a linear cocycle. Okay, so it's a cocycle living in LH, and the other one, the U, is a cocycle living in H. The U is non-linear, and the du is linear. So we start by the linear structure here, and we see that there is a very rich linear structure. Okay? So what do we do here? We say, suppose you have a cocycle, and it's differentiable, okay, on Hilbert space, and let us assume that the ut omega, for t and omega, from h to h, takes bounded sets into relatively compact ones. So it's distributive. Okay, and this fits very well with the Burgers equation and the Navier-Stokes, because both of them has a Laplacian built into the equations, and the Laplacian has a smoothing property. Okay, and so the u takes bounded sets into relatively compact. That's very important, because when we look at the spectrum, we end up with a discrete spectrum because of the compactness. Okay, here is a condition, a technical condition that we require, and it is satisfied by both the Burgers equation and the Navier-Stokes equation. So this is the equation, the condition looks like this. Basically, it says it's a logarithmic condition on the derivative, the pressure derivative. Okay, so that condition is checkable in both cases. Okay, in the Burgers and Navier-Stokes, you can check it. It's not very hard to check, but Okay, now here is the important point. Now what do? Now you say, take the derivative, the pressure derivative at y omega. Remember, this is a mapping, a linear mapping on H. So you can take its adjoint, Hilbert space adjoint, and then compose it with the mapping itself. Okay, so you get a positive operator. Okay, because if you take an operator and multiply it by its adjoint, you get a non-negative operator. And so you can take 1 over square root. You take a square root of 1 over 2t. So that makes sense. Okay, then operator. And then you let t go to infinity. Now, the spectral theorem tells you that this limit exists. The limit exists. Uniform operator no. Perfectly in omega. Perfectly is something that we added in, and the existence in the discrete case goes back to Ruel. Ruel proved that if t is discrete, then this exists. And we managed to show that it's continuous is still true, and even perfectly in omega, which is something you need when you're looking at partial differential equations. You have to look at continuous time rather than discrete. Okay, so the limit exists, and moreover, it is compact. This operator cannot be compact because the reason it's compact because U takes bounded sets into compact sets, and if it's differentiable, then the derivative will be a compact linear operator. Okay? And positive, of course, because this is non-negative. And so the spectrum is, I can write it like this: e to the lambda 1, e to the lambda 2, e to the lambda 3, because I know it is positive, non-negative. So it's e to the something. Okay? And these somethings, lambda 1, lambda 2, or lambda 3, are the so-called Lyapunov exponents. Okay? These are called, by the name, they call them Lyapunov exponents. They give you a measure of how the solution behaves as t goes to infinity, the exponential growth rate of the solution as t goes to infinity. And it's interesting because in this case, because of the ergodicity of the Wheeler shift, these numbers, lambda 1, lambda 2, and lambda 3, are fixed numbers. They are deterministic. They are not stochastic. They are not random. They're fixed numbers. So you can now talk about a stationary solution being hyperbolic or not, because you know these are fixed in space. These lambdas are fixed in space. You can tell which one is positive, which one is negative, for sure. Okay? Without saying, without dependence. If it's dependent on omega, then you have problems. Okay, of talking about hyperbolic behaviors. Okay. Now, so we call them the Lyapunov exponents. These are the lambda n's. Okay, and if you want to write them more formally, you just say take the derivative and take the logarithm, absolute value, not absolute value, the norm in h at y omega, and then take the log and take 1 over t, and then let t go to t. That's really just the exponential growth rate of the derivative of the solution. And what this says, that the theorem says that these exponential growth rates are one of these lambda n's. So it cannot grow other than that. It has to pick up one of those fixed. Okay. Furthermore, if you take a non-zero eigenvalue of the Ruel operator, oscillating operator, it has a fixed finite multiplicity. So that means it has the eigenvalue has a fixed space of eigenvectors is finite dimension, and with a fixed multiplicity mj and a corresponding finite dimensional eigenspace fj omega. The spaces itself will depend on omega, but the dimension, the size of the space, is deterministic. It's fixed. Okay? And so you get this mg equal to. All right, and now we can start with the space H, but then we can break it up into subspaces, into actually a filtration of subspaces. And we can do it like this. You can say En, you add up all these eigenspaces from 1 to n minus 1, and take the orthogonal complement of that, you get En omega, and E1 is H. And then we know the codimension of this is the sum of this, which is finite, it's fixed. And then we see these nested spaces, subspaces of E1 is H, and so you get smaller and smaller and smaller and smaller, and they're random. And each one of these, you pick up one exponent. If you are here, for example, for the linear case, you pick up a particular exponent. If you are here, you pick up a particular exponent as t goes to infinity. So this is a complete description of breaking up the space of initial condition into a very canonical description in terms of the stability of the equation. And so in particular, you, as I said before, if you are in between En omega and En plus 1, if G is there, then you pick up exactly lambda if you are in between. Okay? So it's a really complete picture of what's going on in terms of exponential growth. Okay, and the top exponent, which is sometimes important because it tells you whether you have global stability or not. So if lambda 1 turns out to be negative, for example, that means all initial conditions will die out eventually. Okay? If lambda 1 is positive and maybe lambda 2 is negative, then you have hyperbolicity. You have some paths that go away to infinity and some paths come down to stationary form. Okay, just like in the classical five-dimensional dynamic system situation. Okay, and moreover, these spaces are invariant under the linearized system. So if you take the linearized system and you act on these subspaces, closed subspaces, you generate the same, but at a different theta, okay, at a different omega. So that means the stationarity of this. Okay, so here is a picture. I don't know whether you can see this one, maybe it's not so good. But this time I turn the Hilbert space around like this so that you can see it, as opposed to like that. And then each one is nested. See? So they go like this. This is E1, E2, and so on, and here. And now we are still looking at the linear case, linearization. If you start, say, here, in between E1 and E2, and you follow the equation, the linearized equation, you end up in between. Okay? If you are in the middle, in this big middle one here, and you follow the equation, you come back to the same. Okay? So all these are invariant under the dynamics, so to speak. Okay, now let us try to introduce the idea of hyperbolicity. Now we are ready to do that because we know the Lyapunov exponent, lambda 1, lambda 2 are fixed, so I can decide whether some of them are positive, some of them are negative. Okay, I can make that decision easily because they are fixed and deterministic. Okay, so let us say you have a stationary point, and suppose that the theorem 1 is the theorem I just stated to you. We say that it's hyperbolic if it has a non-zero Lyapunov spectrum. That's a natural definition. Okay? If the lambda ends are non-zero, then you say it's hyperbolic. Okay, now I'm going to show you the saddle point theorem just by picture, because if you write it down, it's kind of very messy, but it's true. Okay, if you can see it now. Okay. So this is the theorem. Now I put the H like that, and this time I put 0 just as to explain to that this is the fixed point is 0 there, okay, because you have a linear map and it's 0 at 0. Okay. So what do? You say we have a subspace that goes like this, which is a contracting subspace. Okay, it's random, that's why it's 0, and this one here is the expanding subspace. Okay, and now if you start use the linearization and you start close to 0 here and apply the linearization, you see this red line here, it goes away from 0. Okay, and now if you are here, or in fact if you are close here, let's put it this way, and you go backward, you are a little bit far away. So part is contracting, part is expanding. Okay, again the same geometric picture. Okay. Okay, now we try to see the nonlinear case. So far we've seen the linear case. Okay, you have this straight line, nice one, contracting and expanding. Now the question is, how does the picture look like if you are looking at the original Navier-Stokes equation? Okay, the nonlinear. You can imagine, you can kind of won't be surprised to think of this because you have a linearization that gives you this saddle picture. When you want to look at the nonlinear case, all you have to do is bend these spaces into manifolds. Okay, submanifolds, local, near the stationary point. That's exactly what's happening. Okay? And when you bend them, the tangent space to these manifolds are precisely the stable and unstable subspace. It's a very nice picture, really beautiful picture. Okay, if you draw it, but if you write it down, it's not so. It's very long, you know. Okay, so here I'm going to just set it up so that you can see. Okay, we are going to use the norm, which is the one I introduced before, CK epsilon norm. And the theorem, the stable manifold theorem, says this, called theorem 2. Suppose you have a hyperbolic, stationary point, hyperbolic, and suppose it satisfies this condition, again, integrability condition. Okay? So this tells you basically that you are near y, near the stationary point, you have to have this logarithmic expectation defined. Okay? It's a technical condition, and it's checkable in both cases. Okay? Then there is a random variable rho and ck epsilon submanifolds of the. Now, what are we looking at here? We're looking at, remember, the y omega is the stationary point. You draw a little circle around it. In fact, you draw a tube around the stationary point, and then within that tube, when you section it, you see these manifolds. Okay, you see ck epsilon manifold, u s omega and u omega. Okay, when you section it, when you slice it. Okay, so let me draw a picture so that you can see it better. So this is the stationary equilibrium, the red one, stationary equilibrium, and this is the tube. So these are circular because they are, you know, radius. They don't have the same radius because the radius is rho omega. It changes from place to place. Okay, but they are stationary. The radii are stationary processes. Okay, and you get this from here. So these are points like this. Okay, this is the tube. Now you want to look near the tube. What is the behavior of the nonlinear flow near the tube? So if you start here, F, this is the point there, and you follow it, and like this in the blue, you might get out of the tube. But at some point, you go in and you never leave. You stay in the tube. Okay? At some point here, you go in and you stay in the tube. Okay? Now, let me look at the slice. Just two slices. Okay? So you have the same picture that we had before, and now these are the circles, two balls. So you see here, this is one of the manifolds, and then this is a stable manifold, the red one, and here it's marked over to this one. Okay. And then this is the unstable, the dotted one, if you can see it, the dotted one, and it goes over here, marks over here. And so you see u omega is unstable, and here also. And then these are the tangent spaces that I told you about. This one here is the tangent space of the stable, that's why the arrows are pointing in. And this one here is unstable because the arrows are pointing out. See? So this is a stable manifold. Okay? It looks very much the same as the finite dimension case, except you have to remember that S omega has finite codimension, and U omega has finite dimension. The instability is finite dimension with a fixed orbit. Okay, and of course this is the U. And now here is the connection with the past. If you are here, you go here closer. If you start on this manifold here and follow the equation, you get closer there. And then if you are here, you go backward and you are closer. Okay? So that's nonlinear. Okay, I think I have time to tell you about the physics. Okay, behind it. Okay. All right. So here is the Burgers equation. This is Burgers equation. It's a one-dimensional. Sorry, I don't want to say it's one-dimensional because it's really infinite dimension. But it's spatially it's one-dimensional. Okay, and in fact we just do it here for the unit interval. This is the simplest case. The physicists love this equation. It's a fantastic equation. They write hundreds of papers on this one. Okay, so very good equation. So we decided to use it somehow, but put something extra. So this part here, added in. In fact, this one also, but this is not a big deal. But this is the stochastic part. You see, unfortunately, we are only able to do linear noise. The question with nonlinear noise is open. We don't know. We don't know what happens. Are the theorems correct or not? Okay. But anyway, this is a Dirichlet condition. At 0 and 1, you get 0. Okay. Initially, you have a function f. Typically, this function is L2 from 0 1. You make it L2. And these are Brownian motion, W1 and W0. Okay, these are Brownian motion. So take a look at the equation because I will move on from here. Okay? And the xi here is a space variable. Okay? And you can see the Laplacian here. And this is a quadratic term that I was talking about before. U times du by dxi. It's really essentially quadratic. And that's really the most difficult one. Because everything else is nice and linear. That's where the nuisance is. And it's very hard to deal with that. And the same thing with Navier-Stokes. You have similar terms. Okay? Instead, you have the gradient instead of the okay, so this is a Burgers equation. And as I said, it is modeled used by many authors to model turbulence in physics and engineering. So the idea is that they want to know what turbulence is. So they use it. Okay, so the noise coefficient is constant. I'm just explaining what I said. W0, W1 are independent Brownian motions. And the noise coefficient, sigma 0, which is, I'll show you which one it is, this one here. This is spatially dependent. It's dependent on the space, okay? But there is no U here. So this is what you call additive noise. But there is a U here. So we are adding this spatial noise, additive noise, and multiplicative noise, this one UT, is linear. Okay? Linear. Now, the term gamma is just a deterministic drift, a linear term, and viscosity is constant. This is the factor in front of the Laplacian, what you call viscosity. And the initial function f, in what's so-called, the physicists will call it the energy space. H equal L2. We call it L2. Okay, Hilbert space. That is, it's called energy space. Okay? And the external forcing is coming from a linear drift, and from the linear white noise, and from the space-time noise. Okay. Okay. So you can do this. So this is the theorem. You can describe the dynamics of the stochastic Burgers equation via perfect locally compacting C infinity cocycle. So here you can construct C infinity cocycle, which will capture all the solutions of the equation at the same time for every f. And the long time asymptotics, almost sure asymptotics of the cocycle are given. Now we can, once we have that, we can apply theorem 1, the first theorem, to Burgers equation, and it gives us this countable non-random Lyapunov spectrum. So it comes as a corollary from theorem 1, the one that I gave you at the beginning when I said differentiate and apply this spectrum theorem. So it applies because the conditions of that theorem are all satisfied by Burgers cocycle. Okay. It's not easy to check, but they are satisfied. It's quite an effort. And then, once you have that, then you can prove the local stable manifold theorem and the local invariant manifold theorem and the global invariant. These all come as corollaries from the same way that you construct the local stable and unstable manifolds. This follow conditions. Okay. So as I said, you just apply theorems 1 and 2, the ones I gave before, which is abstract. Okay, let's say, go back to the beginning, kind of. So you say, if I take f in h, in the energy case, now I'm referring to the Burgers equation. Take f in h, then the solution exists for every f. And this is known. This is a classical. For example, the Pratt-One actually. This is well known. Okay, that if you have any initial condition, you can solve uniquely. Okay. The question is, can you solve simultaneously for all f? Can you get a cocycle that will give you all the solutions when you plug in f for each omega perfectly? Okay, that's something you need to do. Okay, and so here is the theorem that will give you that. Okay, it will tell you that you can actually capture all the solutions by one single cocycle. Once you do that, then you can apply the real ergodic theory. Otherwise, you can't. You can't do it for each f because it's not perfect for each. Okay, so my solutions generate a perfect Frechet C infinity cocycle U theta on the energy space, which satisfies the oscillating integrability condition. So this is the condition, the same condition that we had before, satisfied, except this time you're looking at L2, and H is L2 as opposed to L2. This is the same condition that we had before. Okay, it's satisfied. Okay, let me just give you a little feel for how do you capture the cocycle. Okay, as I said before, the technique of Kolmogorov theorem collapses because of infinite dimension. So you have to do it by hand. Every equation you have to find a way to do it. So here is one way to do this equation. Okay, so you start with QT. So you put the noise in here, W1. This is a linear noise. And then you define the E2 integral with respect to QT Q minus 1. Again, it's a semigroup. Now, TT minus TT is the heat semigroup of the Laplacian. So you put it in there and you make it act on the noise, on the additive noise. Okay, and you get this new random process. It's very nice. This is a nice process. Okay, it doesn't involve the solution. It just involves the semigroup of the Laplacian. And then you say, look at this complicated Burger equation. You see how this looks like? You are looking for the unknown is V0. It's a random equation. It's a random PDE, okay? Because Q is random, okay, and Z is random, okay? But it doesn't have Brownian motion. We actually encoded the Brownian motion inside the Z. And so it becomes just a PDE with an omega in it. And so now you can hit it with PDE technique. Okay? You can hit it with PDE technique. There are a priori estimates you can use that are well established, and you can actually do that. And so what we did actually is we took the stochastic partial differential equation and we turned it into a random partial differential for each omega. And for that omega, you just fix your omega and then do the analysis just like you don't know any probability. Okay, and you get it. You get it right. So here is the connection between the V0 and the Z and the solution of the Burgers equation. And it's just like that. V0 activates this random canonical process, multiply by QT, and you get the answer. Okay? So if you get an estimate for V0, it will give you a corresponding estimate for U. Because this we can control. QT and Z we can control. So, as I said, it's sufficient to solve the random Burgers type equation perfectly in omega, and a unique Mie solution is obtained. You have to prove it from scratch because the theorems are not, there's not a ready-made theorem to tell you that this random equation has a solution. You have to actually do it. And it's not extremely difficult, but it's doable. And you use a contraction mapping theorem argument to do it. Okay? And you can show that the solution is global because of the a priori estimate. So now you can get some a priori estimate. So this is a very standard trick in PDE, is that you get a priori estimates, and they tell you that the solution doesn't explode in finite time. So you have to derive these estimates And you have to look at the equation and do some calculus, essentially, to see that the estimate is correct. Okay? Because you're looking at a random. So this is the type of analysis that's employed here, okay? Without having to go into the actual detail. Okay, and now invariant manifolds. Now let's look how the invariant manifolds apply in this case. Okay. First of all, you want the stationary equilibrium to satisfy this logarithmic expectation, which is a fairly mild condition. It's even less than asking for the moments, because you have logarithm. You say the logarithm has finite expectation. Okay. Then the theorem 1 applies about the derivatives. Okay. You get a fixed spectrum, and the theorems all, the other theorems all work. The theorem for the local stable manifold theorem works, and the Lyapunov spectrum is also exists. Okay? Verbatim. You don't have to do much. As soon as you check this condition, then you just apply that abstract stuff to do it. Okay, let me give you the maybe I'll take a couple of minutes. Is that okay?
Yeah, if you like.
Okay. So I will tell you a little story of the stochastic Navier-Stokes. Okay. So we look at the two-dimensional stochastic Navier-Stokes. As we probably all of us know, that the three-dimensional case is a big prize. Million? Is it million?
2 million.
Few million, 2 million. Yeah, I'm not going to try it. Can't do it. Stochastic, even deterministic. Okay, no? Okay. It's true. Okay, now look how the equation looks like. I wrote it in differential form also, just shifted things around a little bit. The Laplacian, I put it on the left-hand side. Now here is the quadratic. This is the right term. Okay, u, and then times the grad u. It's the quadratic. And then the rest of it is really not too bad. Here is linear, and this is nothing. It doesn't include u, and this is linear. Okay? And this is the boundary condition we have here, non-slip condition, and this is also the Dirichlet condition, and this is the initial condition. Okay? So this is how the equation looks like. It's similar, the noise is quite similar to the Burger case. Linear and then additive space. Okay? Linear, additive space. Okay, now D is a domain, bounded domain in R2 with a smooth boundary. So that's a nice domain in plane. Smooth boundary. And then the U is a velocity. In the Burger setting, the U is a velocity, and it's in 2 dimensions. Okay, the velocity field and position x, time t and x. Okay, and delta is a Dirichlet Laplacian, and ptx is a pressure field, and nu is a viscosity, and w0 again this is a noise, space-time noise, and wk are the linear noise, 1 dimension. You could have them infinitely many. You could have the finite. The analysis is just as easy either way. Huh? Okay? Yeah. Okay, and sigma k, these are the noise coefficients, symmetric matrices, so we assume some kind of symmetry there on the noise, and wk are independent, so the Brownian noises are all independent of each other. And this is the linear part, the derivative, here is the linear part, and the velocity, initial velocity is okay, alpha, indeed alpha. Now, the way we look at this, because we're going to apply Rowell theorem, we're going to put it up in an abstract setting, which is very popular in PDEs, that you put an evolution to, stochastic evolution to. And so that's a very standard setting. And you look at H to be the closure of V, so this is your V, you have this derivative here, which is equal to 0, and then you close it in L2, and that's your state space, so to speak, the H, the closure of L2 of V in this L2 node. Okay? This is the L2 node. So H looks like an L2 space, except you have to preserve the boundary condition. Okay. Keep it 0. So if you do that, then you have the Stokes operator, which you apply the projection now. This is the projection from L2 into H, which physicists call the Helmholtz Hodge projection. Okay, this is the physicist. And then the Stokes operator is just a projection of the Laplacian under this. And the nonlinear term, you just apply the projection to it, and you call it VU. It's still nonlinear, but it's because you are looking. So the evolution equation looks like this. So I just show it to you. So now this equation is in H. Now, see how it looks? A is the operator, B the quadratic, this is the quadratic, and then U. Okay. So this is the equation we are going to analyze. Okay, and apply the ergodic theorem. So first of all, existence of a perfect locally compacting C11. So it turned out to be C11. We couldn't do any better than C11. Generated by all my solution with the stochastic Navier-Stokes. Large time asymptotics are captured by the countable spectrum, non-random spectrum. Just like in the Burgers case, you have a countable spectrum, Lyapunov spectrum. And then the existence of the flow invariant C11, local stable and unstable manifolds. Again, you have them, just like you have for Burgers equation. Yeah, and then you have invariant manifolds also. Let me just show you a picture at the end. I think it will be better to see the picture. Okay, so this would summarize the whole thing. This is the global invariant flag. That means you have the H, and then you have these manifolds. These are manifolds. Okay, finite codimension. And you start in between. They filter the whole space. Start in between. You go in. You there. You go in. Okay. So this is a nonlinear picture for the Navier-Stokes. Okay, I think we are over the time. Thank you.
Other questions?
Well, I have one.
Yes, sure.
Like you had similar graphs, similar picture, a couple of slides before. So, like we had tube, and you thought that when we project, we go in the tube, so it stays in there for the long.
After that time, yeah. After that random time.
How we make sure that it stays in that tube?
Well, this is the theorem.
Is it?
Yeah.
Invariance?
Yes, yes. The theorem says that you can be given that estimate. Remember that funny estimate E, exponential log and so on.
Yeah.
Then you can play with that estimate and control the distance of from that point on of the Cocycle, of the stationary point. And if you say it's less than that, then it has to be there forever. Yeah. But that's the hard part.
Yeah.
So it is less than the radius, right? Less than the radius, the distance
Yes.
between the...
Yes, less than the radius. And it's a random radius.
Is it like the stopping time? Is it very
Yeah, it's like an exit time.
exit?
Yeah. Well, actually, yeah, because no, it's an entry. You're hitting time. So you're out, and then you say how long it will take to hit the tube. And once it hits the tube, then you make sure that the distance of the cocycle from the stationary solution stays below that level for each omega perfectly.
I think our time is expended. Before we thank the speaker again, would like to mention to everybody that we'd be glad if you'd join us for a small reception up on the 3rd floor in the math library. Thank you.